Now we tackle about the practical single-stage vapor compression cycle. The thermodynamic cycle for an actual single-stage system may depart significantly from the theoretical cycle. The principal departure occurs in the compressor. The condenser, evaporator, and piping departures from the theoretical cycle may be kept small by designing the components for small refrigerant pressure losses and by insulating components to reduce heat exchanger with ambient surroundings. In this section, we will especially concern with thermodynamic processes occurring within a reciprocating compressor. So, considering this figure, this is the pressure versus the volume of our cylinder in our compressor. So the diagram is somewhat idealized with respect to compressor valve operation. Because of valve pressure drop, the cylinder pressure during intake, PA, this PA here, is equivalent to P B, and maybe less than the suction line pressure P3. This is lesser than P3 because of pressure losses. And the discharge and the cylinder pressure during discharge, PC, is equal to P D and may be greater than the discharge line pressure P4. This is our suction at point 3 here, and this is our discharge at point 4. Okay. Because of heat exchange between the vapor and the cylinder walls, the thermodynamic state of the vapor at position A may be different from that at position B, and the state at position C may be different from that at position D. At positions B, C, and D, we will assume the thermodynamic state of the vapor and the cylinder to be uniform. At position A, the re-expanded clearance vapor may have a different state than the intake vapor, which just begins to flow into the cylinder at this position. Let us denote the state of the re-expanded clearance vapor as A prime. So for the compression process from B to C, we have this one, the polytropic process, wherein we have the PV to the N is constant. This are in the compression takes place from B to C. That direction from point B to point C. And this is PV to the N is constant. So this one, that is our point pressure versus volume of our cylinder. So example, this is our P4 or suction. This is our P at the P3 is our suction and P4 is our discharge, pressure at discharge. So I'm going to extend this one. So example, this is our point 3 here. Our point T is lesser than. Example, that is our point A, and let's expand this one. This is our point A prime. Or this is B. So by compression, in the compressor, this is our pressure at point 4. So here, this is our point C and D. Okay. That one. So this is PV to the N is constant. Okay. So we have PV to the N is constant. So therefore we have PB VB to the N is equal to PC V VC to the N. Okay, or V is the specific volume in cubic feet per pound, and let us further assume that the temperature change from C to D is negligible. With this approximation, we may say that the VC is equivalent to VD. Okay, for the re-expansion process, so we have here the PD VD N prime this is equivalent to PA VA to the N prime. Prime here. Okay. If we let N is equivalent to N prime, we have this result VA prime is equivalent to VB. So the above analysis with its several approximations establishes a PV diagram. Okay, just like here. So the compression and re-expansion curves are coincident. This is the compression and the expansion curve. This one. Expansion going down and compression going up. Thus, we may conclude that the net work required to compress the clearance vapor in foot-pound per pound is 0. At the end of the intake stroke, or in the intake stroke is in the position B, the total mass of vapor in the cylinder. So the mass total of our vapor in the cylinder is VB over small letter v B. This is the total mass of our vapor. And the mass clearance of vapor is VA prime. No, this is the mass clearance this is V A over V VA prime. So mass intake is the mass intake vapor per cycle this is equal to VB minus VA over VA prime. So since VA prime is equal to VB, then we can write this one as VB minus VA all over V B. So therefore, we have this compressor volumetric efficiency. We have the volumetric efficiency. So this is denoted by N and V. Volumetric efficiency. This is defined as the mass of vapor actually pumped by the compressor divided by the mass of vapor which the compressor could pump if it handled the volume of vapor equal to its position displacement, equal to its piston displacement, and if no thermodynamic state changes occurred during the intake stroke. So our volumetric efficiency would be this one, VB minus VA. VA times this small letter V 3. This is all over VB minus VT times the small letter V B. And this VB minus VA this is equal to VB minus VD here minus VA minus VD. Okay, so looking at the figure, as we here, VB is, this VB is equivalent to, or this VB minus VA is equivalent to VB minus VD minus VA minus VD. Okay, so you have this one. So you have also VA. This is equivalent to VD times the pressure P D over P A raised to the exponent 1 over N. And we have V D. This is PC over P B raised to the power of 1 minus N, since pressure at point C and D is equal and pressure at point A and B is also equal. Okay, let us consider now the clearance factor. We have this clearance factor. denoted by C, we have C. This is VD over VB minus VD. Thus, you can write VB minus VA over VB minus VD. This is equal to 1 plus C minus C times PC over PB raised to the power of 1 over N. So our volumetric efficiency becomes now. This is 1 plus C minus C PC over PB raised to the power of 1 over N times V3 over VB. Okay. So this equation here accounts for the three principal factors which affect compressor volumetric efficiency: the expansion of clearance vapor, pressure drop in suction and discharge valves, and heating of the vapor on the intake stroke. If C is equal to 0, the term in the brackets is unity or equal to 1. So if this C is equivalent to 0 if there is no clearance factor. So the valve pressure drops also contributes to decreasing the term in brackets. The quantity V3 over VB may be less than unity because of pressure drop in the suction valve and because of cylinder wall heating effects. So it also follows from the basic definition of volumetric efficiency that the volumetric efficiency this is M V3 over the piston displacement, where M is the pound per minute pumped by the compressor and PD is in cubic feet per minute. Okay. So if the in theoretical cycle for vapor compression, the volumetric efficiency is always considered as 1. So you have the piston displacement, you have this mass times the V3 this specific volume V3 is the specific volume at the suction point 3. Okay.